Good afternoon friends. Today I will be presenting on dual slope integrating type digital voltmeter. So this is a robust method of analog to digital conversion that is widely used in digital multimeters because of its accuracy and noise rejection. So I am Paavan Binu Mathew, and let's begin by understanding the core principle. So let's go into the core principle. So the dual slope method works in two phases. So the first phase is that it integrates the input voltage for a fixed amount of time, producing a positive slope. Then it integrates a reference voltage of opposite polarity, which produces a negative slope. Because the slopes are integrated over time, random noises averages out and the final measurement will be highly accurate. So it integrates the input signal for a fixed time, then integrates a reference voltage with reverse slope. This process averages out noise, providing accurate measurements. So the three steps are the input integration, reference integration and noise averaging. Here in input integration, it integrates input signal for a fixed duration. In reference integration, it integrates reference voltage with opposite slope, and in noise averaging, the positive and negative ramps average out noise. So let's go into the input integration. In the integration phase, the input signal is connected with integrator circuit. The capacitor in the feedback loop of the op-amp charges at a rate directly proportional to the input voltage. We call this charging time T1. The higher the input voltage, the faster will be the capacitor charges. This phase essentially encodes the input voltage into the input of the integrator output. This is how we go into detail. So in reference integration, after the fixed integration time ends, the input is disconnected and replaced with a negative reference voltage V reference. Now the integrator charges with a constant negative slope. The discharge continues until the integrator output reaches 0. The time taken for the discharge T2 is directly proportional to the input voltage we applied earlier. So in the noise averaging, one of the most important benefit, because the input is averaged during integration. The short-term noise spikes like 50 Hz or 60 Hz AC interference get cancelled out. This is the big reason why dual slope DVMs are preferred in precision instruments, which can measure accurately even in noisy lab environment. Now let's go into the block diagram overview. So in the block diagram overview, the main parts provided here are op-amp integrator, zero comparator, a clock pulse generator, decimal counters and control logic. The integrator does the ramping. The comparator detects when the ramp crosses 0. The counter measures time and the control logic coordinates the phases. Together they form a reliable digital voltmeter. So let's go into the next slide. The integration phase or the input voltage. Mathematically, during charging, the integrator output depends on the input voltage, resistance, capacitance and the fixed time T1. This creates a ramp whose slope is proportional to the input voltage. So stronger the input, the steeper will be the slope. So the capacitor charges at a rate proportional to the input voltage. The output of the op-amp integrator is given by V out is equal to minus V in into T1 by R1C. Here T1 is the time for which the capacitor is charged. Vin is the input voltage, R1 is the series resistance, and C will be the capacitor in the feedback path. So let's go into the discharge phase or the reference voltage. In the discharge phase, the capacitor is discharged by the reference voltage V reference. The important point here is that the discharge time T2 is measured using the counter and clock. The ratio of discharge time to charge time, that is T2 by T1, gives us the input voltage scaled by the reference voltage. This method makes the result independent of the exact RC values of the integrator. So after T1, the input is disconnected and a negative reference voltage, negative V reference, is applied. The capacitor discharges and the op-amp output becomes V out is equal to minus V reference into T2 by R1C. The input voltage is then determined by the ratio of discharge time T2 to charge time T1 scaled by the reference voltage. Here V in is equal to, input is equal to V reference into T2 by T1. So let's go into visualizing the dual slope. Here we can say the constant slope is proportional, where T2, T2 dash and T2 double prime is given. The graph illustrates the charging and discharging phases, showing how the integrator output changes with time. So while we visualize the dual slope, here we can see that the integrator waveform, first a rising slope during the input integration, then a falling slope when the reference voltage is applied. Here the point where the waveform hits 0 is where the measurement cycle completes. This visualization helps us understand how time is being used to represent voltage. So now let's go into the measurement process. This process works step by step. The counter resets and the input integration begins. When the integrated output changes, the zero comparator triggers like control logic to start counting clock pulses. So first the counter and flip-flop are reset. The process is called reset and start. Then the input integration starts and the integrator ramps up. Then the second steps or the comparator trigger, which detects when the integration ends and the system switches to reference phase. Here the integrated output change triggers comparator starting clock count. Then the comparator detects when the integration ends and the system switches to the reference phase. This is known as the reference integration. The counter reaches max, triggers flip-flop and switches to negative VRF. During discharge, the counter measures the time until the output returns to 0. The number of counts directly corresponds to the input voltage. This process is known as the discharge and zero. So let's go into the voltage calculation. The final formula relates input voltage to the ratio of counts during discharge and discharge. Since both are measured using the same clock, the result does not depend on clock frequency fluctuation. This ensures excellent accuracy and stability, which is a key advantage over other methods of analog to digital conversion. The input voltage is ultimately determined by the ratio of counts during discharge and charge periods. The independent of clock frequency, it is given by V in is equal to V reference into T N2 by N1. This ensures accuracy regardless of variation in clock oscillator frequency. Now let's go into the key advantages of this dual slope digital voltmeter. The dual slope method has several strong points. It has excellent noise rejection due to integration. It is independent from RC component tolerances. Auto zeroing eliminates offset voltages. It gives the average value, so no sample and hold is required. And most importantly, it is highly accurate, making it perfect for precision measurements. So the noise rejection, RC independence and auto zeroing are the key advantages of this dual slope digital voltmeter. So let me repeat. So in noise rejection, it has excellent noise and AC component averaging due to integration. In RC independence, the input voltage measurement is unaffected by RC time constants. And in auto zeroing, electronic switch and auto zero capacitor eliminate offset voltage effects. Now let's go into the further benefits. In the further benefits, average value response. It includes better long-term stability and repeatability. So integrated response to average input, removing need for sample and hold circuits. For high accuracy, the high accuracy is high and can be adjusted for specific requirements. Even in environments with significant AC noise, the dual slope DVM continues to perform reliably. This is why most digital multimeters use this principle. So, they are a reliable and precise solution for analog to digital conversion. So, let me summarize and conclude. To summarize, the dual slope integrating DVM is a reliable, precise and noise resistant method of voltage measurement. It's two-phase process, integrating input and then a reference converts analog signals to digital with high accuracy. While it may be slower than other methods or for application where precision matters most, it is gold standard. Thank you.